In this video, we're going to solve this first moment example that is in this playlist, and that's going to be finding the magnitude and direction of the moment at the point O. So this problem is actually more than a statics problem. It's actually more a geometry problem. But these geometry problems are very typical in statics courses. So what I'm going to do, I'm going to define basically a geometric problem, and we're going to use that to solve for the sum of the forces equaling to zero and the idea of moments equaling to zero. So what we're gonna do, we're gonna actually, our goal of this video actually is to define this angle. So I'm gonna draw my axes in this direction. So that's perpendicular to the beam, and that is parallel to the beam. So that'll be x, and this will be y. And our goal of this problem is to find this tension force that is being applied in this direction of the beam. So we're going to isolate the beam. So the forces acting on the beam would be this tension force, the weight of the beam, and the reaction forces at the pivot O. And to solve this problem, we're going to need to know what direction this tension force is pointing at. Since we defined our axes in this direction, we want to actually find the angle that is right here. So this will be parallel to the beam, and we want to find this angle, theta, or whatever you want to call it. We want to find that angle because it gives us the idea of the direction of the tension force, which will help us to solve the equilibrium of this beam. So we can use that to solve this problem. So to find that angle, however, is quite complicated in its geometry, but it can be done. So what I'm going to do first is actually draw out the geometry. So what's almost a given here is that we're given this angle 60 degrees and this hypotenuse really of 5 meters. So we actually could draw a right triangle from going to this point to point O. So that's what I'm going to do first. So it's kind of noticeable when you get to a lot of dimensions in a statics problem. It tries to point you in the direction of how to draw these right triangles or various triangles to help you solve the problem. So that's going to be our first right triangle. And on this side, we also have dimensions going in the vertical and horizontal direction. And we're given this offset, which we have to keep in mind for later. But we could draw a right triangle going from B to O as the hypotenuse, and we draw the vertical distance from here to about here. Sorry about that. And we could draw the horizontal distance to there. So now we have those triangles defined, but there's also one more offset. If you can see right here, there's 0.8 meters from the beam to point A. So actually there's another right triangle, very small, but it's still there, from point O to point A. And we could draw a right triangle going in this direction. So this right here is a very small, long right triangle. And lastly, what we have is this obscure triangle or irregular triangle that lies right here, which we will need to solve for that angle we are looking for. So we just simply define it from B to A. So now what I'm going to do is redraw this shape so that we could analyze it even further. Now that we have this figure drawn, we're going to start defining the dimensions of this shape. So what I'm going to do first is draw this given angle. So this is going to be 60 degrees. We were given this is 5 meters. And we're given, what else are we given? We're given that this small length is 0.8. And what we have here is this height. And if you look at the original picture, the height is actually 9 meters minus this offset of 0.75 meters. So actually this height right here, don't get tricked by thinking this is 9. This is actually 8.25 meters. And we're also given this dimension here, which is 3 meters. And is that all the givens in this problem? I believe so. I don't think there's anything else. So now we're going to start defining our angles. So the angle we're looking for, as we stated earlier, is actually somewhere about here. So this is going to be the angle we're looking for, theta. and we're going to define all the other angles we need right now. So what I'm going to use is a different color, maybe this color, and what we want are basically all the angles that are right here. So if we define this as alpha, this is going to be alpha, and I'll explain why we need these angles right here. I'm going to call this beta, and maybe this is going to be psi or something. Let me draw it out here. And basically, we want all these angles because we know we can find this angle. Because we can find, okay, let me go first by how we find these angles. So this angle right here is simply the tan inverse of this right triangle. This angle right here is the tan inverse of this right triangle. And we can find this angle beta by knowing that this is 180 degrees. So we have an equation to find for beta. And later we can find the dimensions or the hypotenuse of this triangle and this triangle, which can later be used for the law of cosines, and we could use that to find this angle. So that's the whole process of this problem. And so this angle right here is actually psi as well, and that's given by this idea of transversal line. So if this line is parallel to this line, then the angles inside right here and right here are actually equal. And we could later use that to solve some problems. So I'm going to define some dimensions as well. So I'm going to call this h, and I'm going to call this hypotenuse going along here as big H. And that should be everything we need to solve this problem. So let me start off with the angles. So we're going to define psi as the tan inverse of 0.8 divided by 5, as you can see by this right triangle. And we can define alpha as the tan inverse of 8.25 over 3. And now we could define beta. So this will be alpha plus beta plus psi plus 60 equals 180. So we could define beta as 180 minus 60, that's 120 minus psi minus alpha. So we can define beta in this fashion. So now we're going to define the dimensions that we need for the law of cosines. So h is going to be, I'm going to go down a little bit. So this is going to be, h is going to be 8.25 squared plus 3 squared by the Pythagorean theorem. So that's going to be that. And then h is going to be 0.8 squared plus 5 squared square rooted. And I believe that's everything we need to solve this problem. Oh, there's one thing that I did not define, which is going to be useful later, is actually this big angle. We're going to call this a big angle, I don't know, maybe epsilon. So this big angle right here is epsilon, which contains, we could define epsilon as theta plus psi. So that's going to be a very useful equation to solve for this angle theta. So now that we have that, I'm gonna put these values in my calculator and calculate these values. So I'll be right back. So now that we have all these dimensions defined, now we're gonna look at this triangle by itself. So what's very important about this triangle is that we can use the law of cosines. If you don't remember the law of cosines, there's a derivation on my channel. Be sure to look at that. It may help you remember it, or if you're stuck on an exam and you need to derive it for some reason because you can't remember it, be sure to look at that. It's a very simple derivation and it may help you. So we're going to define this triangle, which looks something like this. So this is going to be little h, this is going to be big H, and this is going to be beta, which we defined up here. If you look at that, so this is basically that triangle, and we have all our dimensions. So what we're going to do now is define this angle, which we called epsilon. So by the law of cosines, we could define epsilon by doing h squared, or actually we're going to define this side we'll call it R. I don't know what to call it. So we'll define that side as R, and we're going to solve for R. So this will be R squared equals H squared plus big H squared minus 2H big H cosine of beta. So we're going to define R as the square root of this. So 2H cosine of beta. Take the square root of that, and that'll be our definition of R. So now that we know R, I'll calculate this later, but now that we know R, we could define this angle epsilon by using the law of cosines again. So we could say that H squared, which we know, is equal to big H squared plus R squared minus 2RH cosine of epsilon. So we could solve for epsilon here. This will be, if you add this over and subtract that, so we get 2RH cosine epsilon equals H squared plus R squared minus H squared. And now we can divide by these values. So this will be cosine epsilon equals H squared plus R squared plus or minus H squared divided by 2RH. And we could now define epsilon as arc cosine of this value. So now we have this angle epsilon and this value R. So I'm going to calculate these values real quick. So I calculate the values for R, which is 5.958 meters, and epsilon, which is 105.306 meters. So as drawn in the figure, this is not an exact representation, but it should be an obtuse angle and not an acute angle. So the diagram is not drawn correctly, but we'll keep that in mind when we draw the diagram for the free body diagram. So we could actually define this angle theta, which is what we're looking for, this angle theta, by using this equation. Epsilon equals theta plus phi. So if epsilon equals theta plus phi, so theta, which is the angle we need to solve this problem, is going to be theta equals epsilon minus phi, which is going to be equal to 96.216 degrees. So we have our angle theta defined in this diagram, which is going to be right here somewhere. So this is going to be our angle theta, which is parallel. This line is parallel to the x-axis as we defined earlier. So now we're going to draw the free body diagram of the beam plus this pivot A, because we know that the mass of the pivot A and the beam is 300 kilograms, so we want to include this whole thing, and its center of mass is right here, which is 2.5 meters away from point O. So let's draw this free body diagram real quick so we could define that. So the sum of the force, or the free body diagram, is equal or looks like this. That's the pivot. Here's the beam. So it should look something like that. And we'd say that theta is actually 96 degrees. So if the tension force is actually pointing a little bit in this direction, so it's not perfect, something like that. And this is going to be the angle. This is going to be the angle theta. And we know that the reaction forces on the pin is going to be in this direction. So you could define these arbitrarily, but I'm going to follow the coordinate system that we defined earlier, which is going to be like this. So this is going to be x, and this is going to be y. And that should be, oh, and then the weight force is being applied vertically downward. So this is going to be, sorry about that, this is going to be the weight force. And now we could solve this problem. First, I'm going to define this angle right here by doing the complementary rule or supplementary rule. I forgot which one it's called. But all I'm going to do is do 180 minus that angle theta. So this angle right here is actually 83.784 degrees. So what we're going to do now is write our system of equations. So the sum of the forces in the x direction I'm going to call this, I don't know, big A or something. So some of the forces in the x direction is going to be, this is the tension force. This is going to be the T cosine of A. And then we're going to have minus. So we know that this angle right here, let's see what we define that angle as. We define that angle as psi, I believe. Is that angle psi? No, actually that angle is 60 degrees by this diagram. So the beam is 60 degrees from the horizontal. So we're going to define that right now. So 60 degrees from the horizontal. So this is going to be 60 degrees. And by that notation, this angle right here, this line is perpendicular to the beam, or it points in the y direction. This angle right here is going to be 60 degrees. So now we could define W, so it'll be minus W sine of 60. And then there'll be a reaction force in the positive x direction, so it'll be OX, which equals 0. Some of the forces in the y direction, so it'll be T sine A minus W cosine 60, and then minus OW, which equals 0. And then we could solve for the moment about O. So the moment about O is going to be, we define this as positive. This is in the positive direction based on our Cartesian coordinate system. So this is going to be some of the moments in about O. So the moment is 0 here, and the tension force points in this direction. The y direction actually has a perpendicular distance, which is going to be 5 meters, I believe. So let me see. So this is going to be T acts in this direction, so that'll be 5 meters from the pivot, and the weight force acts in this direction, which is 2.5 meters from the pivot. So we could say that T sine A, the perpendiculars to the y direction of T is going to be 5. So we multiply this by 5. And then we know that the moment for W, this is 2.5. So this is going to be plus or minus. Wait, is this? Yeah, this is positive. This is going to be minus. So minus, and then this is going to be 2.5, and then W cosine of 60, which is the perpendicular perpendicular force from the beam, and then 2.5 is a perpendicular distance from this point to point O. So that should be the only reaction for, or the only forces causing a moment about point O. These forces are not included because there are no perpendicular distance of OX or OY to the pivot O. So since this problem is only asking to solve for the moment about O, we could solve this equation. It does not equal 0 for this case, or actually it might if we include there's a reaction force pointing in this direction, but since this is a pivot, it is free to rotate, so there is actually no reaction force. So this moment cannot equal 0 in this problem. So for this instant, the force that the T is being applied, this should be the moment about point O. So we could say that the sum of the moments about O is going to be equal to this. So we're given that the tension force is equal to 6.3 kilonewtons, so that's 6,300 newtons. The sine of, what was it, 83.784 degrees. This is going to be 5 meters minus 2.5 meters times W, and I believe the weight is 300 kilograms times 9.8. That is correct. So we're in the metric system, so it'll be 300 times 9.8, which is the weight, and then the cosine of 60 degrees. So if we solve this equation, we'll get the moment about O. So what I get for the moment is a positive 27.636 kilonewtons. Since this moment is equal to, or is positive, we defined our orientation in the correct direction. So we call this positive. So that must mean if we're using the right hand rule, the moment vector about O is actually equal to 27.636 k hat, which is in the positive direction, which follows this definition that we defined for the moment. So this will be kilonewtons meters. So that is the solution to this problem. So I'm going to quickly recap what we just did. This is not really a statics problem per se, it's more of a geometry problem. So we defined the geometry. Just be sure to recognize the dimensions and how they can help you define angles and right triangles mostly. And if there's a weird looking triangle that happens to pop up in your diagram, then it's typical that you're going to have to use the law of cosines or either the law of sines. So just be wary of that. So we defined our angles, we defined our dimensions to solve for this angle theta, which was perpendicular. Now, the angle theta is defined from this line, which is parallel to the x-axis that we defined at the beginning of the problem. So our goal was to find this angle theta. So we defined our dimensions, our angles, and used the supplementary rule or the complementary rule. I forget which one. I think it's a supplementary rule to find this angle beta by using these angles alpha, psi, and 60. As you can see in this equation, we used that rule. And then we defined this big angle epsilon as this part of the triangle. And we could use beta and epsilon and these dimensions h and big H for the law of cosines to help us find the angle theta. So that's what we did here. And once we found the angle epsilon, we could use this basic equation epsilon equals theta plus psi to find this angle theta, which is the direction that the tension force is pointing. So then we drew the free body diagram of this beam, and we found the moment about point O by using our basic or the scalar operation of finding moments.